Hello everyone. In this video, we're going to compute the limit of this product as n approaches infinity. What is a common mistake of evaluating this limit? A common mistake here is to distribute the 1 over n to each of these terms. So it's like when we distribute this one, we'll get here over n, and so on, and then over n. And if we look at the powers of e, so they are actually bounded by 1. So the numerators here are bounded by e. And as n approaches infinity, each of these terms, okay, will approach 0. And you might conclude that the limit is equal to 0 plus 0 plus 0 plus and so on, okay, plus 0, which is equal to 0. In Calculus 1, we have a limit theorem that tells us that the limit of a sum is equal to sum of limits, but that theorem is only valid for a finite sum. But in this case, the summands increase as n approaches infinity. So the number of terms here increases without bound as n approaches infinity. And in this case, limit of an infinite sum is not necessarily equal to sum of the limits. So how are we going to evaluate this limit? So to evaluate this limit, let us first write this sum here using summation notation. So we can write it as limit as n approaches infinity of 1 over n times this one can be written as summation from I equals 1 to n of e raised to I over n. And this can be written as limit as n approaches infinity of the summation from I equals 1 to n of this product. So we're allowed to do that because n here is fixed in this summation. So we can treat 1 over n as a constant in this expression. And now here's the trick to evaluate this limit. So this limit here can be considered as limit of a Riemann sum. And this limit can be written as the integral from 0 to 1 of e to the x dx. Why can we write this as this definite integral? Let us recall how to write this definite integral as limit of a Riemann sum. So we want to write this definite integral as something like this, limit, and this is a Riemann sum here. And our function f is f of x equal to e to the x. And if we look at the graph of our function, we have this increasing function here, f of x equals e to the x. And the value of this definite integral is just the area under the curve over the closed interval 0 to 1. And here we can approximate the area of the curve by using circumscribed rectangles. So let's say we want to use here n rectangles. And let's have our rectangles here to have equal width. So let's say the width of each rectangle is delta x. Then in that case, delta x is equal to 1 over n. So here we have this as our ith rectangle. And since this is a circumscribed rectangle, so the right endpoint of our interval gives the height of the rectangle. So that is I over n. So if we consider the ith interval, x sub I minus 1 to x sub I, so our x sub I star, so the value of x that we're going to choose from this interval to determine the height of the rectangle is equal to I over n. So for example, in this first rectangle here, the height is determined by the right endpoint, which is equal to 1 over n. Therefore, by definition of the definite integral, this is equal to the limit of this Riemann sum here as n approaches infinity. And what is our x sub I star? X sub I star is equal to I over n. So therefore, f of I over n is equal to, if we replace the x by I over n, we'll get here e raised to I over n. And our delta x is equal to 1 over n. Therefore, this sum here is just equal to the sum from I equals 1 to n of e raised to I over n times 1 over n. So that justifies this equation. Therefore, we can find the limit of this by evaluating this integral here, and antiderivative of e to the x is just e to the x evaluated from 0 to 1, and we'll get here e to the 1, which is e, and then minus e to the 0, which is equal to 1. Therefore, this limit here is equal to e minus 1. I hope you enjoyed this video. Please don't forget to like, share, and subscribe to help me grow this channel. Thanks for watching, and I hope to see you next time. Bye bye.